Hi everyone, welcome to this video on topic P4, atomic structure. So this is to do with radiation, nuclear radiation, alpha, beta and gamma. So let's just start with a quick recap on Rutherford's gold foil experiment. So you would have learnt this in chemistry, I think it's C2, Rutherford's gold foil experiment. So what Rutherford actually did in order to disprove Thomson's plum pudding model. So really quickly, Thomson's plum pudding model looked like this. He believed that the atom was made up of mainly positive charge. All of this was a positive charge with negative plums dotted in between. Now Rutherford did an experiment with gold foil to disprove this theory. So what he did was, let's say, here's my gold foil. Now remember, gold is an element. It contains one type of atom. So in this gold foil, you would have nothing but gold atoms. So I'm just going to here draw an atom just so I can show you what happened. But this is a gold atom and loads of those are found in that gold foil. Okay. So he shot a beam of alpha particles. Now alpha particles are just tiny particles. Alpha is represented as a symbol like that. He shot a beam of alpha particles at this gold foil, and majority of the alpha particles went straight through. However, some hit the nucleus and reflected back and bounced back. But like I said, majority went straight through. So this told him that actually, well, Thomson's plum pudding model can't be right, because he said that the whole atom is solid. Now, how can all these alpha particles pass straight through if the atoms are solid? It also told him that there is some sort of central charge in the middle, and that's why some of the alpha particles reflected back after hitting that center point, which we now know is a nucleus. So that's his experiment, and the two key points are: atom is majority empty space. That's why the alpha particles went straight through, and central nucleus, and that's why some reflected back. Now, let's talk about the definition of an isotope. Again, this is C2. An isotope, is basically a different version or different versions of an element. So e.g. carbon 12, carbon 13, carbon 14. Now, they all have the same number of protons, so same number of protons, same number of electrons, but different numbers of neutrons. So that is an isotope. Let's focus now on alpha. So alpha particles, the symbol is that's an alpha particle. So alpha radiation, sorry, let me just mention this is nuclear radiation. So we are going to look at 3 types of nuclear radiation. So alpha particle is number 1. So alpha consists of 2 protons and 2 neutrons. So just like a helium nucleus, 4 at the top, 2 at the bottom. Remember, the atomic number tells you how many protons there are. The top number tells you how many protons and neutrons there are. So we've got 2 of each, which makes it 4. So an alpha particle is effectively a helium nucleus. Now alpha doesn't travel very far. It can only travel a few centimetres, and it is stopped by paper or skin. So it can't travel very far, and the materials that stop it are paper and skin. So alpha particles are very large, slow, and therefore we say strongly ionizing. So what that means is ionizing means this particle can bump into lots of different atoms along the way, knocking out their electrons, okay, causing other atoms to turn into ions. Now this is dangerous, especially in the body, because ionization, knocking out electrons from cells or atoms, can lead to cell mutations, can lead to cancer, effectively. So because of the size of alpha, it's strongly ionizing. It moves slow, therefore bumping into lots of particles along the way, knocking out their electrons. Beta particles then, so this is the second one, beta, and this is the symbol for beta. It's like a little capital B with a stick on the end. So beta particles are just fast moving electrons. So they have no mass and a -1 charge. So beta particles are fast moving electrons. So because they're fast moving, they're moderately ionizing. So they're less ionizing than alpha, but they still do ionize. They still do cause other atoms to lose electrons and turn into ions. Now, beta can be stopped by a sheet of aluminium metal. So that's the material that's stopped. So beta particles travel a bit further than alpha particles, but they're stopped by aluminium. So for every beta particle that is released, that is emitted, let's say from a nucleus, so a beta particle is released, which is effectively a fast-moving electron. What happens is one neutron in the atom turns into a proton. So you don't need to know at this stage, at this level, why that happens, how it happens. All you need to remember is in something called beta decay, and I'll go through these in a moment in more detail. Beta decay, from an atom or from a nucleus, one fast-moving electron is released and one neutron turns into one proton. Last one then, so we talked about this when we were looking at electromagnetic spectrum. The third one is gamma radiation. So gamma radiation is a transverse wave, so it looks like that, and they can travel long distances in air and are stopped by lead or concrete. Gamma radiation is weakly ionizing. So out of the three, alpha's the strongest, the most ionizing, then it's beta, then it's gamma, and it's because it travels so quickly, it almost doesn't have time to bump into all those atoms around it as it's passing through. Now let's take a look at alpha decay. So I'll just split the board. Alpha decay and beta decay. There's no such thing as gamma decay, and this is just a little bit of maths really. So alpha decay is basically when you lose an alpha particle from an element. So for instance, if I've got uranium 238, so that's its mass number, that's its atomic number. What happens is during alpha decay, when this alpha particle is lost, remember alpha is a helium nucleus. So what you have to do is you minus 4 from the top number, so 234, and you minus 2 from the bottom number, 90. So when uranium 238 has lost an alpha particle, i.e. a helium nucleus, it turns into a different element, having minus 4 from the top and 2 from the bottom. Now, the question may either tell you what it turns into, or you may have to find it on the periodic table, an element with those two numbers, or the question might just say it's called X. So this is how you would write it, plus helium 4 and 2, and that basically means we started with uranium 238, we lost a helium nucleus, i.e. an alpha particle, and ended up with this new element, and then we've just shown that the alpha particle is lost as well. Okay, beta decay on the other hand, let's go with carbon 14. So beta decay, remember, is when a neutron turns into a proton in the nucleus and a fast moving electron is released. So all you have to do in this case is the top number stays the same, and because one neutron turns into an extra proton, we plus 1 for the atomic number, for the bottom number. And again, this turns into a new element, and let's call it Y. So 14 and 7 plus that fast moving electron that was released, i.e. the beta particle. Okay, so that's just 2 rules. Really, really simple. Doesn't matter what numbers you get, as long as for alpha decay, -4 and -2. For beta decay, you just keep the top the same and plus 1 at the bottom. Now, let's have a look at half-life. So half-life, sometimes you might be given a graph, sometimes you might be given just a worded question. And half-life is basically the time taken, so half-life is the time taken for the number of radioactive nuclei to halve in an isotope. So remember, nuclear radiation, for instance, isotopes are very unstable. So, they're decaying, you're losing alpha, beta, etc. quite often throughout time because of this instability. So that's half-life then. So you might be given a graph. At the bottom, let's say it's time, and I'm just going to put in some numbers. Obviously my graph isn't accurate, but I'm just going with it. 400, 600, 800, 1,000. Okay. So you might be given a graph that looks like that, and it says, work out the half-life for this isotope. So this axis, before I forget, is activity. And activity is measured in becquerels, capital B, lowercase q. And then this one is time in seconds. So what you do to work out half-life is you look for the top of the curve here. So it's at 800 for me, roughly on my graph. 800. Do not use the top number on the graph, because look, my line stops here, so don't use this number. Just be very aware of that. If it was continuing on, don't use the number right at the top just because it's at the top of the graph. You're using the number that's at the top of your curve. Half-life is the time taken for the number of radioactive nuclei to halve in an isotope. So my activity is 800. Half of 800 is 400. So what you do is draw a dotted line from 400 until you hit your line and then go down. This is my half-life, the time taken for the number of radioactive nuclei to halve in an isotope. It's 2.5 seconds according to my graph. And that's all you have to do. Just halve the number that you're given here. If they ask you for a second half-life, you do half of 400 because that's the first half-life. The second half-life is 200. So again, go across with your dotted line. Okay, sorry, maybe my line should have been like that. Go across wherever you hit the line. My second half-life is 5 seconds. And so on and so forth. I think they'd probably only really ask you for 1 half-life or 2. So there's 3 definitions that you need to know, and you need to know what the differences are. So the first one is irradiation. So this basically means when an object is exposed to radiation. So exposed just means that it's in the area where there is radiation. So it doesn't mean that radiation gets in. It just means that the object is somewhere, I don't know, in a room full of radiation. It's just exposed to it. Contamination